ended there with a look at some of the minerals that Arkansas has to offer, and we talked about in the northern part of the state we have the dolomite and the calcite, and kind of in the southwest part of Arkansas, Murfreesboro area, some good things going on there. We have the gypsum deposits that are used in making sheetrock, recall that, and the diamond, crater of diamond, the diamond mine. So the diamond is Arkansas's gemstone. So yes, the diamond is a mineral, but because of its value and beauty, we do call that a gemstone, and it is Arkansas's state gemstone. So having introduced you to the minerals, we are ready now. We're well equipped with a foundation. We looked at the mineralogy, the internal structures, physical properties, and the two very broad categories, the silicates and the non-silicates for our minerals. Now we are well equipped to tackle the rocks. Okay, so materials of the solid earth, our rocks. This is the chapter 2 information. So we do want to go ahead and get started on that. The first off, a nice way to try to categorize our rocky material is to look at the rock cycle. The rock cycle was actually put together way back kind of in the 1700s, early 1700s, late 1600s, by a gentleman named James Hutton. He is the founder of modern geology, our modern way of looking at geology. And he's quoted as saying the present is the key to the past. And in that, and by that, what he means is that we can take a rock today and take a look at it, and we can interpret then the past from it, past environments, living organisms of the past. And so it really can tell us a lot about geologic time, geologic history. So he also came up with this interrelationship between three rock types, categories that he talked about. So the rock cycle does show these interrelationships, and it's going to present some processes that then will make or produce products, our rocks. And so we do want to take a look at that, and it is cyclic in nature, but it doesn't mean that it has to go through each rock type to complete a cycle. It can take shortcuts here and there. So we do want to begin, historically, we just sort of begin with magma, so molten earth material that's completely melted. So the rock cycle, Earth as a system, we did introduce you that in the introductory chapter, where yes, Earth has all manner of spheres, 4 different spheres, but that those spheres do interact with one another, and Earth is a system. So the rock cycle really does help us envision the interrelationships. So magma is where we usually begin. They'll have a diagram here in just a few moments, but it begins beneath the Earth's surface as a molten earth material, completely molten, and then the material can crystallize. So crystallization is our process, and this is when the ions are beginning to form solids. So they're crystallizing out of the magma, and so all those elements we kind of talked about, the ions that we talked about, as the magma begins to cool, we had a definite order that those minerals were going to crystallize out in, if you recall that from chapter 1, our minerals. So crystallization, they're going to start forming solid particles. And so this group is known as our igneous rock type, okay? Igneous, coming from magma, okay? Of course, weathering, transportation, and deposition are some other terms that we use, and that pertains to our sedimentary rock. So say our igneous rock here can crystallize out, and it can crystallize out internally beneath the Earth's surface. We call that plutonic or intrusive. And then it could be extruded through volcanism, so volcanic nature, lava cooling, that can happen and crystallize out. Then the next processes, weathering. So now we've got the rock solidified and it gets exposed to the surface, which it is a surface process, weathering. And this could be the mechanical breakdown or chemical fluids could act on that and break it down. Water is something that's very important in the weathering process, but it gets transported in some manner. Water again, running water, wind, maybe glacial ice, moving that sediment, breaking that down to smaller particles and transporting them. And then eventually they do get deposited, so deposition. They're going to fall out of the water, the wind's going to slow down, and they're going to drop out. Or the glacier's going to melt and drop out all that sediment. So we do end up with sediment from that weathering process, and then transportation, deposition. Then the process of lithification. Lithification is where we turn it to stone. So processes within that are compaction, so pressure, squeezing the material together, and cementation, so some sort of glue that is going to hold our little sediment particles together. And so that will form the sedimentary rock. That's our second rock type. Then the process of metamorphism. So metamorphose, to change, like a butterfly changes from a caterpillar to a butterfly. It metamorphoses. So metamorphism, we do change our rock. What happens with a metamorphic rock is you get more heat and more pressure being acted on it, and even some chemically active fluids as well in that metamorphism process. And it will change the chemical structure a bit within the rock. And so we do call that metamorphism. And that's our metamorphic rock type. Then, let's say we're going to complete our cycle here. Let's say we take that metamorphic rock and it goes ahead, gets buried, and it goes ahead and completely melts one more time, becoming molten magma once again. So now there you are, you're starting back at your starting point of magma. And so we say we've completed the rock cycle. But like I mentioned before, it does not have to go through each and every one of these stages. It can take little shortcuts. So the full cycle, again, does not always take place. There are some little shortcuts, some little interruptions that can happen. For example, you could go through and get your sedimentary rock, but it gets buried and it will melt completely, and then so you're back to a magma again. Igneous rock becomes metamorphosed directly instead of going through the sedimentary stage. Sedimentary rock, which is produced from weathering and lithification, could get weathered again. Okay, so it becomes a different sedimentary rock. A metamorphic rock can weather, so it could become a sedimentary rock. So there are these little shortcuts and very much interrelationships that do occur in our rock cycle. So it's not that one rock has to go through all of the cycle. Okay. But this is the diagram that was just showing in a very nice way all of that terminology that I was just mentioning. And so typically we do start melting going on down here. The earth material has melted. So internally that material is very hot in Earth's interior, and so it has gone ahead and melted, completely beginning to work its way up as heat's trying to make its way to the outer surface, right? It's going to move its way up, and some of that's going to cool. Now, some of that's going to cool internally within the Earth's surface. As it gets closer to the Earth's surface, temperatures are a little lower, and it could actually solidify, crystallize out internally. So those are intrusive types of igneous rocks. Okay, but you could also get through volcanism, a volcanic eruption spewing the lava out to the surface, and so you can also get what we call extrusive igneous rocks as well through that process. So, but crystallization in there. And we get our igneous rocks. Okay. In that process, you see a little water, so it's precipitating there. You're getting the either mechanical breakdown of those particles through weathering, or perhaps they're dissolving in the water. So some sort of chemical process going on in there. Maybe even organisms, animals are doing this as well. Perhaps chemical or mechanical. And that's breaking it down. It's getting transported, so you see the little streams working its way, the sediment, so those smaller particles, those sediments are working their way, being transported to an environment here. Typically we think of an ocean or a water environment where it tends to not be too turbulent so that those sediment particles can deposit, drop out and deposit. And then you're going to get layer after layer after layer of those sediments, and that's going to create the compaction over time, okay, large expanses of time for these processes. So you're seeing here sort of the layering that's happening of the sediment. We call that stratification. So those layers are strata, bed after bed of sediment, and they're getting the cementation. So we do get percolation of fluids getting down in between those particles and end up solidifying and gluing or cementing our rock. So that pretty much turns it to stone in that lithification process in there, lithification process. And you probably can't see that too well, but you do have a copy of these PowerPoints of all the layering. So the sedimentary rocks are quite striking in that all the layering and the amount of time that took place, millions and millions of years for those layers to occur in there. So that gives us then what we call our sedimentary rocks. And then say through increased heat and pressure or chemically active fluids acting on that rock material, you can see a little waviness in that, meaning that's getting compressed, it's under a lot of pressure. This can happen from mountain building, so structural geology will be something, a topic that we'll talk about, how you can get pressure and squeezing in on the material. So yes, heat, much more pressure going on in there, but not to the point that it melts, right? And that can trigger then the metamorphism, a couple types of metamorphism in there, contact and regional, what we'll talk about further. And then, should your rock, okay, go ahead and melt again, then you complete that cycle, we say, and we begin anew with magma, molten material once again. Okay, so that's pretty much a synopsis of the cycle, okay, agents of metamorphism, and the processes in weathering, as well, and of course, the crystallization process in the igneous rocks. And so, in a synopsis, that's the rock cycle, and it's credited to James Hutton, our founder of modern geology. So in turn, we want to kind of take ourselves through each of the rock types, the igneous rocks, kind of take a look at what their mineral composition is, what their various textures are, kind of how we arrive at the classification of our rocks, and we'll do that for each type. But we're starting here with our igneous rocks to get us going here. So of course those do form as magma is cooling, it's crystallizing out to solid form. And again, we talked about that being forming inside the earth, beneath the Earth's surface. Those were known as intrusive. They also call them plutonic, okay? Coming from the god Pluto, Greek or Roman, I can't remember. Pluto, though, he was like the lord or the god of the underworld. Pluto, yeah. So that's where that term comes from. Plutonic or intrusive, we call that. And rocks then that would have formed on the surface through volcanism. So extrusive, a volcanic eruption of some sort. So it's very similar to magma, except with a lava, you don't have all the gases in it. The gas is fizzed out, bubbled out. So lava is similar to a magma, yet the gases aren't in there. I liken this to a can of soda. If you like that carbonated soda, and it's under pressure when it's in the can and the lid's on, or the top of the lid's on. Well, when you release the lid, okay, all those bubbles start fizzing out. Okay, they're no longer under pressure, so all that gas, all that carbon dioxide, bubbles right on out. Okay, and that's similar to what's going on with a magma versus a lava. So similar, but yet the gases aren't in the lava. But we call that volcanic or extrusive. So forming on or very, very near the Earth's surface. That would be the extrusive, so above Earth's surface versus below intrusive on Earth's surface. So in one of those two places, we are getting the crystallization of the magma. And so those ions are arranged into orderly patterns. So whatever the mineralogy is, you remember we had a series of which mineral would come out at what temperature, and we had a series of that we looked at last time. We'll be kind of looking at that again because it's important in the formation of our igneous rocks. So you'll have your mineralogy, your composition of your igneous rock, but we will look at the cooling record. So just how quickly or slowly did our rock cool? Okay, so it tells us something about it. So the crystal size is determined by the rate of cooling. And this will create a variation of textures. You might have some very coarse-grained crystals, you might have very fine-grained, and so we've got a series of textures that we will look at. So the slower the cooling, the larger the formation of the crystal. It has a little more time to create a larger crystal. The faster it cools, the smaller the crystal. But now, if you cool so rapidly, okay, very, very rapidly, you don't even get a chance to create a crystal, and we do call that glass, okay? We'll look at the kind of glassy texture. One they don't have on here is the vesicular, where there's a lot of holes in the texture, and that's attributed to all those gases. So the cooling rate was very fast, and the gases, as I mentioned, were escaping from the magma or lava, and it solidified with all those holes. We call that vesicular. And then there's one where you can actually get two contrasting crystal sizes. It may have began its cooling beneath the Earth's surface, so you got some larger crystals, and then maybe it got erupted and volcanically erupted to the surface more rapidly, and it began cooling at a much faster rate, so it finished its cooling at a much faster rate. So you get a combination of large crystals and small crystals, and that's known as porphyritic. So there are a few in here, and they do mention the porphyritic in there of these. So classification is based on their textures, so what's going on with the crystal sizes and what happened in there, and their mineral composition. Okay, so what minerals are in them. That's very important. So we need to go back to this one. So you do have several textures, and the textures will record or define the cooling temperature or give you a record of that cooling rate. Okay, so the cooling history of the rock is in the textures, described in the texture of our minerals. So we have several here that I can actually show you some examples of as well. We'll kind of put the synopsis together here. But a fine grain is considered an aphanitic They didn't really give you that proper term for it, but it's an aphanitic type of texture. For those of you in lab, you will be learning that term, but for in here, fine grain is okay for us, but an aphanitic. But this is a very fast cooling rate, so you're going to get very small crystals, maybe even microscopically small. You can't quite make them out. The coarse grained is called phaneritic. Again, a term for those in lab that should be familiar with, but phaneritic. And so those are a slow cooling rate. So internally cooling at a much slower rate, those intrusive ones, you're going to get a much larger crystal grain in that, to the point that you can pick out the individual minerals in the rock. And I do have a good example of that if I can find it. Here it is. Okay, I have a phaneritic camera under here. So what I have here is a granite. Okay, I know we haven't quite gotten to our names yet, but within the granite, you're seeing some lighter kind of pink coloration, a little bit of darker in there, pinky, and some darker of that smoky quartz, let's say. And so, individually, I have the minerals. So I've got the feldspar, if you remember feldspar, the quartz, that smoky quartz, the hornblende or that amphibole, okay, of our minerals, and silicate minerals. All of these are silicate because they're coming from magma, right? And these have come together. We can see these individual mineral crystals within our igneous rock granite. So that's a phaneritic, a very large crystal size that you can just pick them out. And I've got one here that's very, very large. Also had a bit of mica in it. You see the pinks, and this is sort of the pinky part here. These are those mica, those sheet silicates we talked about. Huge pieces of the mica in there. So those crystals, very large crystallization, very large, very slow cooling rate. So that's a phaneritic, very coarse grain. You can actually pick out the individual minerals in the sample. A good example of a phaneritic. Okay, porphyritic, two varying crystal sizes, and so like I mentioned before, I've got one here called andesite, and we'll learn about those names here in a bit, but the white in here are a little bit larger crystals, and then you end up having some much finer, darker kind of crystals in the background there. These larger white ones meant a slower cooling rate. Those little tiny black ones in there, or the grayish ones in there, that meant that it kind of finished its cooling at a much faster rate. So it had two contrasting cooling rates, and so we call that porphyritic. There was one in there that they called glassy. Okay, got some obsidian here. Obsidian, it didn't even have a chance to make a crystal. So its cooling rate was so very fast that it didn't even get a chance, the ions didn't get a chance to form a crystal. So it's sort of an amorphous solid in there. This one's known as obsidian, as we'll see how they're classified, but glassy type of a texture. One they don't mention, but I've mentioned it. We will pop this one under here. This one is pumice, and this one is the one that has the frothy or the holy kind of appearance to it. It's the vesicular texture. So this would be indicating that when it cooled, it was at the surface and all those gases kind of bubbled out, and it kind of froze those bubbles in place and left all these holes in it. So you're seeing all the vesicles in there. And so that texture is known as vesicular. I don't think they quite mentioned that in our PowerPoints, but that is certainly a type of texture. And the glassy, yeah, was very, very fast cooling rate. The porphyritic that I mentioned with the andesite there, 2 crystal sizes. So it had 2 rates of cooling. And so really, depending on your cooling rate, that's going to dictate how we classify, how we name. Mineral composition is the first consideration, and then the cooling rate, the texture, is the second consideration. So you can get a variety of igneous rocks in this manner. Here was an example of the fine grain texture. I didn't pop one of those under the camera, but yes, this is a rhyolite. Very, very fine grain. We would need a little magnifying glass or a microscope to even see the individual crystals. This sample right here, called rhyolite, is the same mineralogy as that piece of granite that I showed you, but yet we can't pick out all the individual mineral crystals in it because it had a much faster cooling rate, giving it very, very small, almost microscopic crystals. They're in there, the mineralogy is in there, but yeah, we can't make them out just by the naked eye. Okay. Here's our piece of granite again. So you're really now able to pick out individual mineral crystals in there. So you can see more of the composition of this, and a coarse grained texture, and that was called the phaneritic texture. Here's the porphyritic. I showed you that piece of andesite that had 2 contrasting types of cooling rates. That was called porphyritic. And then so this is the obsidian, the glassy kind of texture to it. That is obsidian. Okay. So here we are with our igneous compositions of the silicate minerals. So we did spend a lot of time last time in chapter 1 talking about the silicate minerals. Okay, so the composition of our silicate minerals, we had a series that would happen. And that was all according to how they cooled. Some of them came out at much higher temperatures, and then we had our end members down at the bottom of the feldspars, and then eventually quartz. Silicon dioxide was our last silicate mineral to go ahead and crystallize out of a magma. So that's what this is part of. We are starting with a magma. It has all of those ions and elements mixed together in a molten mixture, and then they're going to start crystallizing out. Okay. So we've got the 2 major groups within our silicates, and remember we have the darker ones and the lighter silicates. If you recall, I talked about those darker ones having the magnesium and the iron metal in them, and so in their chemical composition. So that made the minerals darker. Okay. So we do call those, I mentioned it before, and they're probably going to mention it in here, our mafic type of minerals. Then you have the lighter silicates. So then, as the magma continued to cool, well, all those other metals, the magnesium and the iron, had all reacted out and crystallized out. So what was left in the remaining melt began crystallizing out and didn't have the magnesium or the iron in it. Okay, so we had the lighter silicates, the potassium, the sodium, and the carbonate, so our feldspars began crystallizing out, and they were much lighter in color. Like I mentioned, I showed you the feldspar was sort of a pinky color. It could also be white. The micas would come out, the muscovite micas, the lighter one, the calcium plagioclase, the sodium plagioclase feldspars would come out. And then the last end member is that pure quartz, the silicon dioxide. So those are lighter in color. So 2 major broad categories of those silicate minerals. That's why we talked about them last time. But we call the granitic, so granite-like rocks, the mineralogy of the ones that have the feldspars in them, the muscovite mica, like I showed you, and the quartz in those. Maybe they got a little bit of the hornblende in there as well, but composed mostly entirely of those white silicates, the quartz and the feldspar. So we call that felsic, standing for the feldspar content mineralogy in it, and of course the silica as well. So we call that felsic. Okay. So that represented example of a felsic rock is granite. That's like our good common rock in there. Very high silica content, about a 70% of the quartz material in there. So a lot of quartz in these. That would be a granitic rock. And the granitic rocks are the composition of our continental crust. So it is a granitic type of mineralogy basically in our continental crust. We think of that as a granitic type of a rock. Basaltic rocks, on the other hand, these contain substantially dark silicates. So these do have the magnesium and the iron silicates in them. So they're darker. So something like a calcium rich, so on the calcium side of the plagioclase. And it likes to bump ahead on me. Calcium rich plagioclase feldspars can also have more of the amphibole, more of the pyrrhocene, so those darker minerals. It's known as mafic because of the magnesium and the iron, which the Latin word for iron is ferrum, or ferrous. Yeah. So putting those two words together, they call it mafic. But we can also say basaltic because the common rock is basalt. So looking at the mineralogy of these, we've got some common rocks in there, really just kind of separating them between dark and light minerals. The basaltic rocks are the composition of the oceanic crust. So it is a basaltic type of mixture of mineralogy and rock. And so they're very different, the granitic and the basaltic. And so the oceanic crust and the continental crust, for plate tectonics, we're getting close to our talk about plate tectonics. Because of those great differences between them, they are, when they do interact, we're going to have some interesting things happen that we'll be looking at later. So here's the example of the basalt, and I've got all sorts of things over here I can show you as well. And then we had already kind of looked at a granite there. But some other igneous compositions. So that was sort of the extremes. We had the darker minerals, basaltic. We had the lighter minerals, the granitic. Now these are sort of some other combinations in there. An andesitic combination is sort of in between. It's got a little bit of dark and it's got a little bit of the light, but it's kind of an intermediate mineralogy composition. So andesitic. Common volcanic rock is andesite. Andesite, the name of the Andes Mountains in South America. The Andes Mountains is just full of this andesite. So that actually got its name, the Andes Mountains, because of the rock that is in the mountains that were built up there through igneous activity, through the volcanism. So we do get the andesite stemming, the Andes Mountains stemming from the type of rock that it contains, and so the andesite. And then this one here, the ultramafic. So the ultramafic means that it is really those first minerals that come out of the magma. So the olivine, way up there, the pyroxenes, the next one that comes out. So it's ultramafic, the ones that really have a lot of the magnesium and iron. Those are the first ones that do crystallize out of the magma. We call that representative peridotite. And peridotite is the rock that came up here in Arkansas with a crater of diamonds. So historically, Arkansas did have some volcanism, no longer. But that ancient kind of volcanic neck that we have, these rocks did come up with that volcanism, and the periodotite is a good representative of the ultramafic. This classification chart's pretty nice. I think I'm going to pop my one from the book because it has little pictures of the rocks included in it. So I kind of like this a little bit better as far as because it's showing you a sample of these rocks. And then I can also pop my samples under there as well. Okay, so in trying to classify our igneous rocks, we've got, yes, we want to look at mineral composition. Reach that way up there. Mineral composition across the top. And so you might not be able to read it very well, but in your book, page 52 in your book, in the 8th edition of the book, it's listing the mineralogy. So what mineral composition these do have in them. And so on the granitic side, our representative granite there, of the felsic, remember these were the lighter colored silicates, and so we've got a lot of the quartz and the potassium feldspar in there, and then there are some accessory minerals as well. You can get the muscovite, some biotite, some amphibole in there, but basically it's a quartz and potassium feldspar mineralogy, okay? The intermediate one, so we got amphibole and pelagioclase feldspar, the main ones, and some accessory minerals as well, but an intermediate kind of in between in our silicates. Basaltic, so a lot of pyrocene in there. The pelagioclase, the calcium side of the pelagioclase feldspar, so the darker ones in there. So the darker silicates known as the mafic mineralogy, the darker silicates. And then, of course, the ultramafic, well, olivine's the first one that comes out, and then pyrocene, so it's got a lot of that in it, very, very dark. So you do look at them, and you can see that, yeah, that's pretty light in color, and then we've got some of the intermediate darker, so you got some dark and light mixture. Then you're starting to get a little darker here, and then you're really, really dark with the periodotite or the ultramafic. So looking at the mineralogy or the composition is first, and then we get our names of our igneous rocks by their textures, so their cooling histories. What happened to their cooling histories? A rock in here, you could have the exact same mineralogy, but yet the cooling rate was different. You get a different name for your igneous rock. So, you know, a rock could have the same mineralogy, but because of its cooling history and rate, you give it a different name. And this is the basis of the classification of our igneous rocks. And so, those terms again, off on the side here, texture is this, so the coarse grained, so the larger crystals, very slow cooling rate, so you can actually kind of pick out some of the minerals in there, okay? These are all across the top, this mineralogy, so a lighter side of the silicates, an intermediate mineralogy, more of a mafic mineralogy, but because we've got coarse grained, okay, we give them their certain names. And so this would be a granite, a diorite, a gabbro, and a periodotite, okay? Then if you look down to the next cooling rate, a fine grain, so this is a very fast cooling rate, very, very fine grained texture to it. You can't really make out the individual minerals. But down this row, these have the same mineralogy as a granite, but yet the rhyolite, we call that, very fine grain. So granite and rhyolite mineralogical are the same. but because their textures do vary, where'd my rhyolite go? Had it. Oh, here it is. Okay, so right here, the granite, very coarse grained. Right here, the rhyolite. So same minerals in those rocks, same composition, but yet because their cooling rates differed, we call them different rock names. Okay? So this would be a granite, coarse grained. This would be a very fine grained rhyolite. Okay? And then they mentioned one down here, the porphyritic. So this would be one, a granite porphyry. Okay, it's got two contrasting sizes in there. And then the glassy. So we showed you the obsidian, and it has the same mineralogy as the granite does. Okay, but yet here's the obsidian. It cooled so fast. Okay, that it didn't even get a chance to make any crystals whatsoever. So we call that a glassy texture, and the name becomes obsidian. Obsidian was actually, Native Americans used this to create their arrowheads. It's a very sharp substance. I thought I had some somewhere. Some arrowheads. I keep losing my things here. Here we go. There's a little arrowhead of the obsidian. And they used to use those and trade them, almost like money or something. But they would use those. Obsidian also has an interesting history in the drink. I don't know if you've ever imbibed in tequila, but tequila actually translates into a cutting stone or a very sharp stone, and it has to do with in Tequila, Mexico, where they do make tequila. The workers that were out there harvesting the agave plant that gets fermented and made into tequila kept cutting their feet on the rock, on the obsidian rock. And so the town, the drink, tequila, is named after obsidian right there, and it is. It's very sharp. Even in like cosmetic surgery, they use obsidian because it's very, very sharp. Okay, so a little bit about obsidian there. And if I was to look down just a little bit further here on our table, the pumice. Okay, so it actually has that vesicular texture in it right here. Vesicular texture. So the little holes in it, this cooled really rapidly at Earth's surface and created a bunch of little holes from the gases that were escaping. So our pumice stones, I've got a pumice stone here that we like to use. It's very good for exfoliating the skin, right? And also, pumice-powered lava soap. I don't know if anybody has used those, that brand of soap, but see how it's got pumice-powered, so it's got the ground-up pumice in it. Really takes grease off your hands very well. But lava is the name of it. This is all stemming from the igneous activity, the volcanic activity, and the creation of a pumice, right? The rock pumice. So, yeah, geology, even in the soap that maybe you use, or the pumice stone that you use. So, again, geology is everywhere. Yeah, so that's sort of the composition of a granitic or felsic type mineralogy, but we call them different igneous rock names because of their cooling history. Those textures are different. Yeah, andesitic would be sort of an intermediate. We'd call it a diorite. If it's coarse grained, we'd call it an andesite. I think I showed you the andesite, but the diorite is here. Maybe it's here. I have so many things over here. Diorite at the then, oh yeah, diorites here. Okay. Right there. And then the andesite, now the andesite I had was a porphyry, the one that I showed you, because it had 2 cooling rates. But there is andesite that is just a fine grain, we call it. And that one had the porphyry, was the sample that I showed you of the andesite here, andesite porphyry. So this one actually had 2 cooling rates with 2 contrasting sizes in it. So that would be an intermediate composition mineralogy and how we get those names. And then the last group there that we'll be concerned with, the mafic or the basaltic, so more of the pyrrhocene, the darker minerals. We get a gabbro if it's coarse grained, comparative to a fine grain, which is called a basalt. Okay, so the gabbro and the basalt. Here's my basalt. Here's my gabbro. Okay, so the basalt, very fine grained. There, and here's the gabbro. The gabbro, you can kind of make out some of these darker pyrrhocene, okay, in there, the darker one. The plagioclase feldspar, so like that calcium plagioclase feldspar, that one that has that sort of blue iridescence in it. I don't know that that's going to show too well, but you can kind of make out those little individual mineral crystals in the coarse grain. Okay, because it had a much slower cooling rate, those minerals were able to get a little larger crystal size. And here's the basalt, same mineralogy as your gabbro, but it's very fine grained, so we call it a different igneous rock name in there. And then you can get porphyry, so where you had sort of 2 cooling rates, you could get a basalt that had porphyry, exhibiting porphyry. Okay. And then so periodotite, these are like rare or uncommon, they say, with different cooling rates, because pretty much you're going to have your periodotite or your olivine and your pyrrhocene be really beneath Earth's surface, so you're not necessarily going to get too quick of a cooling rate with those. So that's sort of a synopsis of your igneous rock classification. It's a nice chart. It's really good to kind of go back and review that. But yeah, you can have the same minerals, okay, mineral composition, but because they have differing cooling rates, we call them different igneous rock names. And so that's a synopsis of how this is put together. Okay, let's see that. They may take us through that little series of how the minerals do come back out. Yes, back up real quick. So that was a chart in your PowerPoint you have, but also on page 52 in your book. There's one that has the pictures of the rocks in it, which I think is really nice. So how those different igneous rocks are forming. We've talked about this in our silicate minerals in chapter 1, but we didn't really call it anything special. But this is what it's called. It's called the Bowen's reaction series. So this is how the minerals are crystallizing out sort of in that order, and it was all according to the temperature that they would crystallize out. So magma is crystallizing out over temperature ranges, several hundred degrees, right? So our mineral crystals will come out in a predictable order, right? We got the olivine first, then the pyrrhocene, then the amphibole, and if you so on and so on, right? The biotite, and so forth, coming through. Feldspars, and then the quartz at the end there. So they will come out in a predictable order. Your last minerals to crystallize out are, of course, very different from the first ones to come out. It's kind of how we had our darker silicates, our mafic ones, magnesium and iron, and our felsic ones, more of the feldspar and the pure kind of quartz, the lighter ones. So we got those 2 kind of separate groups in there, but they are going to have very different compositions, so because they react out. So you wouldn't get, any pyrocene in with your quartz, right? Because their temperature differences of when they crystallize out are so different, so that you wouldn't find those together. But this is, in a nutshell, the Bowen's reaction series. Again, temperature regime, so very, very hot temperatures down to still pretty hot, 750 degrees Celsius, but cooler, and we are talking about magma, so very hot temperature molten rock material, enough to melt your rocks. So the olivine was the first to come out, the pyrocene, the amphibole, the biotite mica, and then all the while those plagioclase feldspars from the darker calcium to the lighter sodium rich. And so all manner of minerals in between there. Potassium feldspar, kind of that pinky salmon colored one. The muscovite mica then, the lighter mica, and then of course the quartz comes all the way out. So these were our igneous kind of types. We had the ultra mafic, the peridotite. We had the basaltic, mafic, so basalt is a good example of that. Andesitic, intermediate, so remember the Andes Mountains, andesite, yeah, in that, and granitic, so the felsic, more the feldspars and the quartz in that. That's really what we did talk about, although we didn't call it the Bowen's reaction series. We did talk about how the minerals did crystallize out in an order to them. You might spend some time looking at that. It's a very interesting chart. And so this is what's occurring as the magma does cool. So you can get actually some pretty complex magmas, like I mentioned, because as some of these crystallize out, maybe they're going to settle back down to the bottom, right? They might just come on out, settle out, sink to the bottom, and so you can get some very complex kind of magmas happening. They might go and sink to the bottom, and they might melt again. So you can get some rather interesting and complex magma differentiations to occur. Okay, so those were our igneous rocks. Now, one that they didn't make a distinction on, but we actually have a good resource of here in Arkansas. I don't know if any of you have heard or been familiar with, but near Little Rock in Arkansas, we have what we call Granite Mountain. They call it Granite Mountain. It is actually not granite at all. It is syenite. So syenite is very similar to granite. Pop this under here real quick. Syenite is what I'm saying on there if you need that. So syenite, there's sort of a lighter version of it, and then I've got a darker version right here as well. Both of those are cyanites, but the mineralogy of a syenite is similar to a granite, so that's probably why they mistakenly called it granite. But the syenite does not have quartz in it. A granite must have quartz in it. It has mostly quartz in a granite. But the syenite is very similar. It does have the feldspars and a little biotite and different things like that, but it does not have the quartz in it. And so our syenite, so just south of Little Rock, they call Granite Mountain, has no granite at all in it. It is actually the igneous rock syenite. So again, it's one of those mafic kind of rocks, but yet it does not have, a felsic type of a rock like a granite, so a granitic type of rock, but does not have the quartz. And so they make that distinction, and we call that syenite. You'll see this, a lot of gravel that they use, they'll mix it in with the gravel. It's very beautiful, kind of a bluish hue to some of them, sort of decorative, but they use that a lot. They grind that up, so not Granite Mountain, it's syenite. And also, you'll see a lot of this. I don't know how many of you have been on that new, kind of somewhat new, Highway 530 on your way to Pine Bluff, let's say. If you look off to the side, they've got lots and lots of rocks in there. They're trying to prevent weathering and erosion of the land material there. So they put all these rocks up there. Well, that's cyanide, so you can impress your friends that you know that that rock is cyanide if you happen to find yourself on Highway 530 on your way to Pine Bluff in there. So that is the synopsis of our igneous rocks. Okay. Next group are the sedimentary rocks. And so we do want to take a look at that weathering process. That's the process that will take a rock, and it could be any of our rocks, and break them down into smaller particles. We call those sediments, okay? And so it could be a couple of ways of weathering. One we call mechanical weathering. This is the physical breakdown of our rock material. Could be the animals, burrowing kind of animals, or plants getting in there and destroying and breaking apart some of that material. But water does play a very big role in weathering. So water is just a wonderful substance in the earth sciences. But frost wedging, so the freeze-thaw cycle of water. Water can get down into little cracks and crevices in the rock and really break it apart, because as water freezes, it expands, and so it can bust apart the rock. So the freeze-thaw cycle, that's known as frost wedging. This next term, your book uses a few different terms, but the term unloading, I think they use exfoliation in your book, and it might be a little easier to remember exfoliation, kind of like our skin. We exfoliate our skin. But what's happening with exfoliation or unloading is that slabs of rock are going to peel away, and this has to do with reduction in pressure of the overlying rock, and it gets eroded away. It's like it's sloughing off. So rock can get heated up and will expand during the day, and then at night it can cool down and contract a bit. So that cycle of being heated up and then contracting as it cools can slough off and peel off, kind of, we call it exfoliation, as a mechanical type of weathering. And I had a few pictures of some domes, some exfoliation domes. We've got one from California, Georgia, and Texas here. What we call exfoliation domes. So these are granite, kind of outcrops of granite, and they go through that kind of heating during the day and then cooling at night. And a rather famous one here, if you've been to Yosemite National Park in California, this was called Half Dome. Half Dome is an exfoliation dome, a granite dome. And it's very interesting. It looks like one side has just been shaved completely off. And it has through the process of glaciation. So a glacier in Earth's history had come through and actually eroded off that half of that dome there. We do call that Half Dome. That one's out there in California, Yosemite National Park. This is also a symbol that a clothing line uses. The North Face clothing line, if any of you have jackets and clothing from there, or mountain gear, they sell mountain gear as well. But the North Face, what they're talking about is the North Face of Half Dome, this exfoliation dome. And that is kind of their symbol. They'll have that little kind of symbol of Half Dome. So we have a clothing line, maybe you didn't know that, named after an exfoliation dome. So geology is everywhere, let me tell you. You just gotta look for it. Another one, Stone Mountain Park, Georgia. So it's more of a pink granite, where they have carved, right into there. I think it's a Confederate memorial sort of carving that they've carved right into the side of Stone Mountain, Georgia. A very large, beautiful exfoliation dome. So we've got some there in Georgia. And this one here, the Enchanted Rock State Natural Area in Texas. Again, sort of a pinkish colored granite this time as well. Enchanted, so it's kind of, history kind of has a mystical sort of background to it. The Native Americans would comment that this mountain at night would have these creaking and groaning, kind of crying sounds, unexplained crying sounds. So this enchantment they would talk about. Well, a geologist comes along and says, no, this is an exfoliation dome. And because of the heating of the day, the rock has expanded, and at night it's cooling, so you're getting movement of the rock back and forth, and that creaking and that groaning sound is actually due to the contraction of this rock overnight. So exfoliation dome right there, kind of took the fun out of it, but Enchanted Rock. And that one's in Texas. And so these are all examples of some exfoliation domes, so like our skin, exfoliating. This is one way that rocks can weather, okay? But California, Georgia, and Texas were some good examples of these outcrops of granite that were exfoliation domes. Okay, so that's one way. The term they use is unloading, but exfoliation is another term for that your book does use. And so here we go. Yeah, that's showing it very nicely here, where you can see that those slabs will just fall down, and you'll get a bunch of that broken up, these little talus of the material that's forming those rock fragments at the base there. They also show the frost wedging process there of water getting into the cracks as well. So frost wedging and unloading of an exfoliation dome. Two pictures there that are nice. These are all mechanical forms of weathering, okay? We're trying to break down our rock material to smaller particles. So mechanical weathering, I mentioned, biological activity, animals can burrow, roots of plants can really do a number. If you've got trees and you've got a nice concrete sidewalk, over time as those trees are growing, the roots of the trees, they're gonna buckle up your sidewalk, and you're gonna have to pay for that to be replaced. So yes, another good example of mechanical weathering. A second type of weathering is chemical weathering. And again, water does play a very large role in this as well. It can actually dissolve away some materials. So this will alter that internal structure of the mineral, removing or adding elements to it. I think I had some, if I can find it, I've got a lot of stuff. Yeah, here it is. So kind of a process of weathering here, chemical weathering over time, breaking it apart. I've got a series of some things here. First off, I have some fresh cyanite, okay? We'll set that like this, okay? So that granite mountain really is cyanite. So I've got some fresh cyanite here. And so over time, we've kind of altered the cyanite so it's exposed to the weather, water rushing across it. So it can begin to kind of alter the cyanite, continuing, breaking up, getting some sediments, because it's just destabilizing the mineralogy, and we end up with some kind of end products of our cyanite. Here's one, we get the bauxite, that aluminum kind of oxide, Arkansas State rock, bauxite, and this one over here, kaolinite, so a clay. So it's really breaking down that cyanide into individual little mineralogy in there and getting some end products. And so that's sort of a chemical. It's really working on it chemically and breaking that down. So a chemical kind of process in there. Okay, so really kind of destabilizing, removing or adding some elements into it. So water, again, very, very important. So, and well, here we go, some more. Yeah, water is the most important, like I mentioned, agent in chemical weathering. So you can get reactions happening Dissolution by acids could work on it as well. Remember, we do have some of those that are, acid will work on them and break them down, dissolve them even. Clay minerals are the most abundant and stable product of chemical weathering. And so I showed you the cyanide sample where kaolinite, which is a clay mineral, very stable. So it will kind of be like an end product of the weathering of a cyanide, let's say. So very abundant there. So we end up, some form or another, through the weathering process, we end up with smaller particles of our rock. It gets broken down into what we call those sediments from the weathered products. Very large group of rocks here. The expanse of them is the greatest. 75% of all the rock outcrops on continents, including right here in Arkansas, are sedimentary rocks. A great place to see sedimentary rocks here in Arkansas would be the Ozark Mountains. So I'll just pop my little map under there as well. But yeah, these are the most common outcrops across, the United States and stuff. But right here in the Ozark Mountains, this would be a fantastic place, northern Arkansas, to go see sedimentary rock outcrops. Beautiful in northern Arkansas there. So the Ozark Mountains. The Ouachita Mountains has it as well, but really beautiful layer outcrops you'll see in northern Arkansas, the Ozark Mountain region. It's great. But yeah, here in Arkansas, you're probably going to bet that you're going to be seeing sedimentary rocks here. We have a little bit of the, like I mentioned, the igneous, so the granite mountains, really not granite, it's the syenite, okay, which is igneous. The peridotite that came up with the diamonds at Murfreesboro and the Crater of Diamonds State Park, a little bit in there. So we have a little bit of the igneous, but we have a lot, great abundance of the sedimentary rock. That would be the most often kind of encountered rock here in Arkansas. Right, so what do we use? Why this group is actually very important in helping us decipher then Earth's history. So used to reconstruct much of it, of Earth's history, clues to past environments. And so when we can get a rock, let's say, that has a fossil in it, that can really tell us something about past environments, give us clues to past environments. If we get a trace footprint or something in it, we can tell something about what organisms lived here. Yeah, they do often contain fossils. But even if we didn't have a fossil in it, something like mud cracks, let's say, or water ripples left behind can tell us something about the past of a, oh, here we go. Like I said, I have so many things over here. And here they are. So this first one that I've got is showing mud cracks. I don't know, well, that's trying to come in. These little cracks along here. So this can kind of give us an idea that this area that this rock came from maybe could have been a tidal flat type of thing where there were a lot of watery type environment. I've got another one here that actually has ripple marks left behind in the sediment, in the sedimentary rock there, kind of got frozen in time. So here's one with some ripple marks in it, a waviness to it. We'll get that to kind of focus. But there is sort of this waviness to that sample, okay? Rippling kind of effect that water, active kind of water would make. So a watery environment that lets us know. This one that I have here with the square, little tiny square on it. These are little tiny salt crystals. You remember the halite, the salt, very cubic in shape? So these kind of got frozen behind here. Little salt crystal casts, we call those, C-A-S-T, cast. Okay, got left behind. So you know you had some sort of a salty water, and then it kind of crystallized out. The water evaporated, crystallized out. So it can really tell you something about a past environment. And so we actually do have some clues that we can get. In southwest Arkansas, I keep mentioning that we have the gypsum deposits. That's an evaporite type of a deposit as well. So water evaporated off and the calcium sulfate, the gypsum, was deposited. So just seeing that we have those gypsum deposits and knowing how they are deposited in the first place lets us know that we had sort of an inland type of a shallow seaway here in, well, at least in southwest Arkansas, but in other places as well across Arkansas. But that gives you a clue to past history. And furthermore, they actually found some dinosaur fossil footprints very near those gypsum deposits. And so again, that does tell us, well, dinosaurs roamed here in that area, probably taking a nice little walk along a sort of sandy beach area near an ocean type environment, an inland sea. So really can give us clues about past environment for sure. So sedimentary rocks really become a fascinating category because of the fact that they can tell us so much about past environments. And sedimentary rocks really were a lot of how our forefathers of the geology field were able to come up with the geologic time scale, which tells us about Earth's history, where we study the present. So the present in the rocks right now is the key to the past. James Hutton quoted that because that is what he was talking about. We can look at the rocks and be able to tell something about the geologic past. It becomes very, very important to us in providing clues. Some economic kind of importance that we have. Coal, of course, is a sedimentary rock as well. If you remember, we kind of talked about the process of coal formation. You had to have a swampy, kind of a bog type environment for the coal to form. So where you have coal beds, you know you had a swampy bog kind of a past, geologic past. The petroleum and natural gas, so we do have important economic status because if you recall the sandstone and the shale, that's where we were getting all the natural gas and the oils because of the pore space. So those are also of economic importance, and those are sedimentary rocks. Sources of iron and aluminum, so the bauxite, Arkansas, the bauxite miners from the introductory chapter, that has an aluminum ore in it, aluminum oxide in it, so it's useful for that. And then the iron as well, a lot of the hematites minerals in that ore of a rock, a sedimentary rock. Yeah, we need the iron from that. So they can be of economic importance as well, our sedimentary rocks. Very fascinating group. So here's how we classify our sedimentary rocks. Two broad groups of textures. So we don't have so many textures like the igneous rocks did with all their different grained sizes there. We just have two broad textures for our sedimentary rocks. It makes it kind of easy for us. So the first one we call the detrital rocks. Okay. So through that weathering process, you're going to get pieces of the rock broken down to smaller, of course, particles. Well, based on the particle size of the sediment, we will classify our detrital sedimentary rocks. It's one branch of the sedimentary rocks. And so according to size, and we don't really need all the details of size. There's a table in here that will give you the detail. But a shale, remember our shale, the Fayetteville shale we talked about in the introductory chapter? Most abundant, of course, but it's very fine grained. It's fine grained, very small pore space in between it. If you remember, I mentioned that it was sort of an impermeable layer. So here's some shale, sedimentary rock of the shale. Very, very fine kind of pore space in there, fine grain. Sandstone, a little more gritty. Brought my sandstone. So it'd be a sand-sized sediment. We'll pop these under the camera. But gritty, sand-sized, okay? We call that a sandstone. And then you can get some very large pebbles and even larger gravelly, pebbly size, called a conglomerate. So those three they talk about there. Let's put those up under the, there's a conglomerate. Here's a nice sandstone. I've got all manner of, sandstones can actually be quite beautiful. Look at the coloration, if that shows up. Yeah, well, I hope it's showing up. And here's a shale. So very, very fine grained for your shale, a particle size. A sandstone, sandy size. The coloration in there, so these are rocks, and so they have gone through the sedimentary rock process of lithification. So you're getting some fluids that get down in between all this sediment grains. That's the weathered kind of sediment there. And it will, of course, through compaction and then cementation, if you remember that. Well, you can get a silica or you can get an iron oxide that kind of glues those sediments together. And so it gives this beautiful colors. So that reddish brown kind of color in the sandstone is due to the iron content of the cement that's cementing it together. So you get the layering and the beautiful coloration of the sandstones. Quite extraordinary. So that'd be sand size. And then look at these big old, it's just kind of a hodgepodge of varying sizes, but they get cemented together into what we call the conglomerate. There is like a siltstone, different sizes, but siltstones are kind of hard to come by. So those are some pretty nice representatives there. So that was the detrital rocks, okay, based on sediment size. And so on this classification chart, you see the coarse grained, yeah, call that a conglomerate. If your gravel fragments have angles on them, so they're kind of sharp, what that can tell you? That can tell you something about a past environment or a past history of your gravel, because if it has those sharp angles still on it, that means they didn't travel very far before it got deposited. So water came along, moved the sediment along, and then deposited it rather quickly. So that it didn't have time for the wave, the water action to kind of roll it along and smooth out the edges. So we call those that have those angular fragments breccia. Okay. Sand size, so you'll get a sandstone. That would be the rock name here, sandstone. Well, it's fine grained, and again, it's, you know, it's got a certain distance, measurement for that, a siltstone. If it's very, very fine, you'll get what we call that shale. Okay, so a siltstone and a shale is kind of hard to tell apart because it's really, it's fine grained. So, okay, so that's the detrital sedimentary rocks. That's one category, and they're based on sediment size. Okay, so that's the particle size. Okay. Then we do take a look then at the chemical sedimentary rocks over here on this side, and these are where you could have a particular mineral that's this chemical mineral, okay, something like a calcite. Then what would we call that? What if the mineral was quartz? What would we call that? What if it was gypsum? What would we call it? If it was halite. What would we call it? And then altered plant fragments. What would we call it? Okay, so that's sort of what's going on with composition. Okay, this one was grain size, particle size. This one is composition becomes primary in the naming of the sedimentary rock for these. So yeah, and I've got some pictures or samples of some of these. I might show you. Get them all. Okay. So here's sort of the crystalline limestone. I may just set them all up together after we get through our list. But calcite is going to be your main mineral composition, right? So find a coarse grain, we call it a limestone, okay? If you get that in some cave type settings, we call that travertine in there. Can be beautiful colorations mixed in them. So some limestone and travertine, coquina. Where'd that one go? Here it is. These have, these are again all calcite, but here we have shells, fragments of shells loosely cemented together. So this is a coquino. I'll lay them up under there here in a second, but little fragments of shells, so organisms that have died, and then their material gets broken, kind of broken down. And various size fragment shells cemented together with calcite, fossiliferous limestone. I had some like that as well. And then the coral. So coral is a little limestone or a calcite material. And if you think about the formation of our beautiful white sandy beaches, like at the Bahamas and in Florida, those are coral beaches. And the way those form are through the work of a little beautiful organism here, the parrotfish. Picture of him here. Pop him under here real quick. The coral fish. Oh, is that going to show up? I don't know. Here it comes. But the parrotfish has this chitinous sort of mouth. There's his eyes, there's a fin. Very beautiful in color. But they will chomp on the coral, okay? They're eating the algae kind of that's in the coral, and then that will go through their digestive tract, and so as their excrement or their waste product, they are creating the sediment that forms the beautiful white, powdery, kind of sandy beaches that we all love to go visit. But think about that next time you're out on the beaches of a coral sand type of a beach. The work of the parrotfish, that chitinous-like beak to it. That's really fish poo, so they don't tell you about that in the brochures. But yeah, we do get varieties of limestone in here. So here's some limestone with coral. And, here's a shell that goes with it, but all of this sort of biochemical, they call it, because organisms have secreted the calcite. And here's that coquino sample. Little fragments of all manner of shells. Yeah, here we go. I think the color's coming in a little better. But these are all little pieces of shell fragments that got cemented together, okay, in our sort of limestone category in there. But calcite was the main chemical composition in that, the travertine and the limestone. So calcite, kind of a big group in there. Chalk, so like even the chalk that I'm writing on the board there. Very microscopic shells, we talked about that, algae, secreting little shells of little microfossils, and then chalk, right? We're spewing those out, billions of those. But very microscopic shells, so microscopic organisms secreted a calcite shell and then created these. You can get huge cliffs if you think of the cliffs of Dover near England. So the White Cliffs of Dover, those are all chalk deposited layers there, microscopic organisms there. So this kind of category, if living organisms were involved, was a biochemical limestone. Okay, and so then we have some fine grain there of the limestones. So calcite, though, is your main chemical that helps us get our sedimentary rock name. If we had a quartz in there, you can get what we call chert or flint. We've got some of that. They actually made arrowheads out of chert and flint, for that matter. Native Americans would use that, but we have that very pure, if you remember, I talked about that very pure microcrystalline quartz, and that is novaculite, right? The novaculite. We have a very good quality of the novaculite. But that is a chert. Those under there. Let's get this guy out there. Might be confusing things a little bit. Chert, yeah, is the light colored one. All novaculite. And flint is the darker. But again, they're both the silicon dioxide or the quartz. So novaculite. I'll write that on the board. Okay. Novaculite, very pure microcrystalline quartz that we have here in Arkansas, in that hot springs area. My map is under here. Real quick. There's hot springs. Sediment all over the place. But right here in the hot springs area where we have all that wonderful hot springs quartz, if you remember that, and then that very pure novaculite, they call that. But that's kind of the lighter color. They made stone implements like arrowheads out of that. Novaculite, yeah, there. That's the chert, okay, the lighter one. And then the darker one is the flint. Okay, that's well. But the mineralogy is the quartz with a silicon dioxide for those two. Okay, gypsum. Okay, calcium sulfate dihydrate, if you remember that about our gypsum. You can get the rock gypsum. So gypsum is one of what we call those evaporite deposits. I'll write that on the board maybe. Evaporite deposits. Okay. Gypsum, so water, okay, will have the calcium sulfate in it, all these minerals in it. And when the water evaporates away, so an evaporite deposit, gypsum will be left behind. So we do know that in southwest Arkansas that we did have because of the gypsum deposits that we have, so gypsum, that at one time Arkansas was covered in an inland sea, okay? And so that's why we've got the gypsum there. We can tell something about then our past environments because of the types of rocks that we're seeing. So they do give us clues to past history. This region as well in southwest Arkansas was, let me go to it here, the location where they found the dinosaur footprints. And if I can get it to work, I have a little clip of the dinosaur tracks that were uncovered in Arkansas. This was back in 2011, where they actually found some, and they had investigators from Fayetteville, University of Arkansas, Fayetteville there, that went and studied the area, made casts of the dinosaur footprints, and so yeah, we had, you know, an inland kind of a shallow seaway, all the gypsum deposits. So what you see in the background are those gypsum deposits, and then the footprints that they're going to talk about here. So we'll see if we can get that to play for us here.
Dinosaur tracks were discovered on private property. Researchers say what they found gives them a better idea of what happened millions of years ago. There's more proof that dinosaurs once roamed our area.
This one's kind of tough to see. I think this is the tip right there.
Lots of people do this their entire lifetimes and don't walk into something like this.
It all started with a phone call from a man in southern Arkansas. He told researchers at the University of Arkansas he thought he found dinosaur tracks on his property.
It was perfectly obvious that they were indeed dinosaur tracks.
So this summer, a team of researchers from the U of A traveled south to uncover a piece of history.
We know a dinosaur stepped on this exact spot 110 million years ago. That's really cool.
There's quite a few dinosaur trackway sites across the United States. It's somewhat unusual to find dinosaur tracks in Arkansas.
The researchers say there are multiple tracks made by several different dinosaurs.
And the tracks are different sizes, and there's parallel tracks that are going the same direction that are clearly made by two different individuals.
So why did it take millions of years for them to be discovered? Paul says Arkansas was very different when dinosaurs roamed the earth.
This particular time, southern Arkansas really was at the southern margin of North America. This particular environment was a very broad coastal mudflat.
That means their footprints were made in the muddy water. Over time, they would get buried by sediments. Researchers are no longer at the site. Instead, they're putting the data they collected together so they can share with all of us what it was like when dinosaurs called Arkansas their home.
Okay, so a coastal mudflat is what they described the area as in southwest Arkansas there. So coastal meaning an ocean type environment, so an inland kind of a sea. You saw the mud cracks. Again, they could get the mud cracks from there, so they know it was a watery environment. And then the sediment of the evaporite deposits of the gypsum. That's also another clue that this was a watery coastal type of an environment. And so those dinosaur footprints, and it was a three-toed footprint, that's known as a trace fossil. It's not actually that they found the dinosaur bones or anything to where they could identify the type of dinosaur it was, but it appeared to be a bipedal, so it was walking kind of upright. He did mention that there were like at least two of them, so perhaps they traveled in groups. So the stride of the dinosaur, so you know, could tell you something about the size of it. We call those trace fossils, and you're going to find those in your sedimentary rocks. Again, telling you something about past environments, and even the animal behavior. It did travel in pairs at least, if not in a group. And so that little clip there, that was very exciting, that we did find dinosaur tracks here in Arkansas. But since then, the people who own the land there have actually dug through those. So it was a good thing that the team from Fayetteville did come and get the casts of those so that we at least have that data to work with. But we wanted that gypsum because of the building industry, right? We make sheetrock out of that. So yeah, a treasure to me might not be so much to another person. So, and it didn't seem to be to the person that owned it there. But that again is a gypsum deposit, a resource that we do have here in Arkansas. Highlights, so if your main mineral is sodium chloride. We just do call that rock salt. I have something here. I'm from Kansas originally, so this was interesting to me. But the halite or the rock salt, so it is just turned into rock. So big aggregates of these can be called rock salt. Got a sample here where halite or sodium chloride has crystallized out. And I went to a little bit like this, a salt mine in Kansas, where I'm from. So if you happen to find yourself in Kansas, this is a great place to go. It's called Stratica, Kansas Underground Salt Museum. So Stratica was a very interesting name because of the layering, right? The strata in our sedimentary rocks. It was very interesting that they called it that. But it's a mine that you can actually go down in and tour. It has a museum in it. So salt, very hygroscopic, so the air was very dry in there. The salt will absorb any moisture, so low humidity. No pests, no organisms can live in there because it absorbs all the moisture. You need water to live. So, but they created a museum beneath there where they would store old films from movies, costumes from like Superman costumes, Kansas, of course. I'm trying to think of the name of that one. No, I'll think of it later probably. But many costumes from film because of the low humidity. It preserves things very well. That's some rock, and you can go down and they'll let you take a sample of it. But this is all halite, and we call that rock salt. So that is pretty much just salt, but a rock aggregate of it. When you get it in large parts like that, they do call that rock salt. The altered plant fragments, so the bituminous coal. Remember that we did talk about several grades of coal, and they gave them some different names. The bituminous was one of them, but even before the bituminous, we had the lignite. And if you recall, I did mention that the lignite, we have a resource of lignite here in Arkansas in the Warren, Hampton area. Is that under there? Again. Well, here, Monticello here, Warren and Hampton area, we had that resource of the lignite coal, but we don't actually use it because it wasn't cost effective. But to get coal, you have to have had in the past environment a swampy, bog-like environment. And so we know that this area in Arkansas's geologic past was a swampy, bog-like environment. So the clues that we can get about past environments are in our rock bed. And so yeah, we had some of that lignite here, but the one they put was the bituminous coal. The anthracite coal is actually a metamorphic rock, which we're going to get to our metamorphic here in just a minute. But yeah, so coal beds do originate in freshwater, kind of coastal, swampy bog situation. So again, I can tell you a lot about that. So that lignite here, maybe we'll put lignite right here. That one was about 40% carbon, but in South Arkansas, that Hampton Warren area. Okay, which is called the Gulf Coastal Plains here in Arkansas. Gulf Coastal Plains. So again, having these deposits, so having that coal gypsum in our area that we're referring to tells us definitely something about, sort of in the southwest part of Arkansas, we had those gypsum deposits. Right off over in here, where they found the gypsum deposits, and over here where they're finding the coal deposits, does let us know that the area was a Gulf kind of coastal type of a plain in Arkansas's geologic past. So things that we can learn from our sedimentary rocks really do. We can look at the present and give us a clue and a key to the past. And so sort of a low-grade coal was the lignite, right? Bituminous, a little higher carbon content. Of course, the anthracite, a much higher. So we talked about that in the introductory chapter. Okay. And again, I mentioned that the Ozark Mountain region is a great place to see the stratified sedimentary rock, the strata or the layering that is very telltale of our sedimentary rocks. So that's the chemical sedimentary rock, that texture, and that's the basis of how they name those rocks. What's going on with the composition in this case? Over here is not the composition, but it's the texture. What is the grain size? That's going to give you your detrital sedimentary rock name. Okay. So that's sort of a synopsis of the classification of the sedimentary rocks there. And you might want to look at that chart and study that. Here we had a piece of the shale, so very fine grained detrital sedimentary rock that actually had a nice plant, looks like a fern fossil in it. So we do get fossils, and it would be in our sedimentary rocks. Would be our best bet to get a fossil in it. And there's a sample of the sandstone, the beautiful coloration. You can really get some exotic coloration going on in there. And again, that had to do with the glue, the cementation fluid. Was it iron laden? Was it silica laden? What was it that was percolating through and gluing those together? So the reds in there are from an iron cement. Okay, the conglomerate, yeah, the large pieces, a hodgepodge of them. The coarse-grained one is a conglomerate. So two groups based on the source of the material, classifying the chemical ones now. So we've looked at that chart already, but this is sort of your background information on that. So derived from the material that was once in solution, again, water is very important, and then it would precipitate out, or in some cases, the water just gets evaporated off and gets left behind. So directly precipitated as a result of a physical process, so evaporation, something like that. Or through those life processes, so those little organisms that had secreted their shells, and then the coquina or the fossiliferous kind of limestone, so something biochemical in nature, so an organism played a role in that. So chemical rocks here, limestone, which is the most abundant chemical rock, lots of that. Microcrystalline quartz, precipitating out of the silicon dioxide or the quartz, so we got the chert, the flint. I didn't show you a piece of jasper or the agate. The agate could be banded and have a beautiful variety of colors. I think we showed you some of that in the mineral unit when I was showing some of the quartzy things. But yeah, it's the quartz minerals, the main one. Evaporates, such as the rock salt or the gypsums that we talked about, and then coal. So those coal deposits can tell us something about that lignite that we have, something about, you know, the past environment, clues to past environments in there. So very, very interesting. And we did mention the parrotfish that does its number and creating the beautiful coral beaches, right? Breaking that down. So fossiliferous limestone. So this is showing up better than my sample that I had, but you've got the fossils in there and they get cemented together. That's fossiliferous limestone. the rock site, so an evaporite type of deposit, the rock salt. So then again, lithification, those loose sediments are transformed into solid by the lithification process. So compaction and cementation. So it could be the pressure of the layer after layer after layer, compaction, pressing down, and then some sort of glue or cement. Calcite can be one, right? And all that limestone, we got the calcite going in. Silica, so the silicon dioxide, a quartzy material, or the iron oxide, so that iron material giving the beautiful reds and the brown colors to a lot of our sandstones. So, but that lithification process, compaction and cementation. So, some features in our sedimentary rocks, the strata is like the most characteristic, are the strata in it, most commonly associated with sedimentary rocks, the strata. And the bedding planes separate the strata. So you can have a history of episodes of deposition. So we're going along, we're depositing, and then you can get a little break in the deposition, and then you get resuming of deposition. So you get little breaks, separate strata, known as bedding planes. So it can tell you something about, okay, how many years went by for this deposition event, and then maybe some erosion happened, and then you get more deposition, so the bedding planes. Fossils. So fossils are most commonly found with the sedimentary rocks, and they can certainly help us determine past environments, as I've shown you here. Are the most important what we call inclusions. So they get included in the rock. The rock is like forming around the fossil, okay, in there. Inclusions. Used as time indicators, so we can match up, rocks from one place to another, and that can say, okay, these are the same, and so we know they formed here at a particular time and way over there, talking great distances, at the same time. So they can be used as time indicators, so really can tell us something about the past in creating that geological time scale. So being able to match them up, using them as time indicators as well. Okay, so that's kind of a synopsis of the sedimentary rocks, okay? And what can be learned from them, especially if we get fossils or if we get fossil tracks, like our dinosaur, our little three-toed dinosaur there in southwest Arkansas. So we can learn about the past from that. Okay. Our last category, if you're still hanging with me, the metamorphic rocks. So these are produced, of course, you could have any of the other three rock types. It could be another metamorphic rock, it could be a sedimentary rock, or it could be an igneous rock. But in some way, they were buried to where they were exposed to more heat, maybe more pressure, chemically active fluids, so the agents of metamorphism they were exposed to. So you take a rock, any of those other types of rock, and then expose them to more heat, more pressure, okay, and even chemically active fluids. So unlike the pressures and temperatures from which they had formed. And so a lot of times these will happen in mountain building. So with the structural geology, we're going to learn about mountain building, and a tremendous amount of pressure is occurring when that does happen. So you can get varying degrees of metamorphism, so a low grade of metamorphism, and we'll kind of go through a series here, but say you had a parent rock of the shale, which is a detrital sedimentary rock, right? And it undergoes more heat, more pressure. The metamorphosed product, or the daughter product of that, becomes what we call a slate, okay, in there. You can really get different degrees of these, and a high grade of that obliteration of the original features And so, yes, you can get quite it, but not to the point that it melts, right? Because that would be igneous again. But it doesn't melt, so. Different degrees of that. Okay. So the settings that we get metamorphism, contact metamorphism, or thermal, they call that. That is where if you do have some magma and it gets close by it, there could be enough heat from that it would contact your rock and actually cause enough heat change that you're going to get some metamorphism to occur. And something I have here is a rock. You can see it fairly well. That this material out here was a granite, and when this finger, almost looking finger-like, intruded, this was magma, okay, this was a magma in here, and it intruded into this existing rock, and the heat from it actually changed the surrounding rock, metamorphosed it into a nice, we call that, rock. It is a nice rock. But yeah, that intrusion kind of fingering in was molten magma. So we do kind of call that contact metamorphism. And this is where it would actually get very close to a nearby magma, okay? Enough that it was hot enough to actually go ahead and metamorphose the surrounding rock. So changes are driven by a rise in the temperature there. Regional metamorphism, as I mentioned, the mountain building, the tremendous amount of pressure that's under. So high pressures, directed stress of the mountain building process. You can get metamorphism from that as well. We call that regional metamorphism. Okay? And that's going to produce your greatest volume of rock, but it's regional. So it's not contacted so much, it's regional pressure there. So that's going to create the greatest volume of metamorphic rock. But there are your there's all the metamorphic agents. So heat can be at pressure, we call that stress. It could be from a confining, so if maybe it got buried, plates moved, you get burial. Differential stress during the mountain building, the squeezing together, and chemically active fluids. Water, again, mainly water, and then this is going to promote crystallization by ion migration, so it's sort of going to recrystallize your minerals that are in there. And so we'll take a look at some of these. But again, with our metamorphic, we've got two broad textures that we talk about with these. Okay, so they're going to show us the origin of pressure. So a confining kind of pressure, meaning coming in at all different directions, confining pressure. And then here, like during mountain building, a differential, so it's squeezing in on it. And you're getting the wavy kind of undulation happening. Pretty high grade metamorphism with that. Okay, a couple different types. So our textures, two broad categories. One's called foliated, the other non-foliated, right? So if it's not foliated, it's non-foliated. Foliated texture. The minerals, through that extra heat and pressure, they're going to realign in a parallel kind of alignment. All the minerals in there are going to want to line up, okay, perpendicular to the compressional force. Okay, so perpendicular to the compressional force. So what if your compressional force is like that? They're going to line up this way. So that's foliated, and they tend to look a little layered and look to them. The non-foliated textures, this is equidimensional. Okay, so the crystal, the mineral crystal in there is just going to be equidimensional. No preferred alignment. So it ends up looking like a coarse-grained kind of igneous rock, actually. It's not. But it looks coarse-grained like some of our granite did, coarse-grained. So foliated and non-foliated. And we want to take a look at the foliated first. So this is showing you, here we have a piece of diorite in there. a mineral that has dark and light, so it's kind of a intermediate type of a mineralogy in it. So like a diorite would have that. And so you're seeing the dark and the light minerals in the igneous rock diorite. And then over here, this has undergone differential stress, so compressional kind of stress in there. And look how it now looks banded or striped. Those minerals have realigned themselves in a preferential order according to the stress, the pressure that was on it. So it really did realign the minerals in there. That's actually a pretty high degree of metamorphism or foliation in that picture there. But we do go through kind of a series of metamorphism, and they'll talk about a few here, and I have a picture, and I'll try to find my samples there somewhere. But foliated rocks. So if we were to start with a parent rock of a shale, which is a detrital sedimentary rock that you've seen several times, can't put my hand on it at the moment, but that shale, like the Fayetteville shale we talked about, let's say we start with that detrital sedimentary rock and it gets buried, so it's going to undergo some metamorphism. Okay. Under moderate or low grade metamorphism, that would create a slate, we call it. Slate is a fine grained, but it's much more dense than the shale would be. It's compacted. It's had a little more heat, a little more pressure on it to compact that. So this would be, I'll put them all up there under the camera in a minute, a slate. Okay, so low grade metamorphism with that. Fine grain, splits easily, a slate, kind of a chalkboard, good for that. We use those in roofing tiles as well, kind of nice. If it undergoes a little greater, there's actually a step in there that this one isn't showing, the progression of it, but here they're jumping ahead to the schist. So a little stronger heat, a little more pressure, so a little more metamorphism occurring, strongly foliated, we call it kind of a platy texture to it. Here would be some schist, okay, so more platy to it, okay. I'll put these up under there in a second. And of course they base those on what kind of minerals are in it. So say you had a lot of mica in that, it would be called a mica schist. I also have some garnet mica schist called starlite. I'll show you that too, but we'll go through our little progression here. So after the slate, we got the schist, and then squeeze the schist out of it, and you'll get a nice rock. And so next would come the gneiss. See all the banding, okay, on that. Dark and light minerals kind of separated and preferentially lined up, okay. So different degrees then metamorphism, increasing metamorphism, foliated, right? And your grain size in there as well. Let me switch over to the camera. Hopefully this is going to show. Maybe not the first one too well. Yeah, my shell's not showing up real well. But let's, I think I've got one of each of these here. Okay. So if we had that parent rock of the shale, not showing up too well. A little moderate metamorphism, you would get a slate out of that. Here's kind of the slate. Kind of fine-grained, much more dense than the shale would be though, it's been compacted more. And then there's one intermediate in there, the phyllite, which they didn't talk about in there, but the phyllite would be one. Almost starts to look wavy you know, to it a little bit. So that'd be an increase in the heat, an increase in the pressure on that for the phyllite. And then we've got increasing again here the schist. And so I've got a, let's see, where would we put that? I don't really want to cover the names up too much. But this one's the starlight that I'm talking about, because it has some granite or garnet in it and some mica in it as well. So they happen to call that one a starlight. But this one is a schist, a mica schist. So it has the mica particles in it. That just preferentially get to reposition and realigned in there, a mica schist. And then the gneiss was the last one, banded kind of appearance to it, and that is pronounced gneiss, the Gneiss. See all the banding? That is a high grade of metamorphism, so it really underwent a large heat and pressure to realign and actually separate the light and the dark minerals out of there. So these are some examples of different varying grades of metamorphism and what the rock names would be. And it's based on the foliation or being foliated, the realignment of the mineral ions that were in there. Okay. A granite will also undergo metamorphism. A little sample of the granite here. So familiar, should look familiar with our granite. Let me turn that over exact here. So if we took our granite, right, and you could see the variations of minerals in there. Of course, we have the quartz in it. We've got that pinky color, the feldspar in it. Some of the darker, you might be getting a little bit of biotite or maybe even some hornblende or amphibole in it. So the mineralogy of our granite, which is an igneous rock, right? A coarse-grained igneous rock. But if that undergoes metamorphism, and this is pretty extreme metamorphism, you see you get the line, the banding, the rearrangement of those individual mineral crystals. And so this one would be called a gneiss rock, the Gneiss, gneiss. So the little geology humor is, I may be nice, but don't take me for granted. Gotta love the geology humor in there. So that is different degrees of foliation, right? So metamorphism, increasing metamorphism, and you're getting the difference in the foliation, and there's your rock names. Okay, so that's one texture. Now the other texture for metamorphic rocks is usually we have a single parent rock with some singular type of mineral in it. It might be a limestone, it might be a quartz or something like that. So here we have if we took and had the parent rock of limestone, okay, let me write that down for you. Say our parent rock is limestone. So remember, limestone is a chemical sedimentary rock, right? And that's like our parent. You could also maybe use a dolostone. Remember how dolostone is that calcium magnesium carbonate, right? And limestone is a calcite. So calcite is basically our mineral, the calcite. You get the metamorphic product of marble. Right, so you've got that, see single kind of mineral, and it really will look equidimensional. So we had some of the limestone, and let me compare it to the marble. Grab my, know about the location. Lost some of the limestone, I guess. Too many rocks over here. But marble. So if you have that fossiliferous limestone in there, and it's probably buried somewhere here. Yeah, well, at least I have this one here of the limestone, okay, as our parent. And then, which is calcite, is the mineral in that. And you pretty much under heat and pressure, you recrystallize and make them crystals even a little bit larger, so they become a little more coarse-grained with the crystal of calcite in there, and it creates the metamorphic offspring or the daughter product of marble. So calcite is that main ingredient. We can do this with the quartz mineral as well. So maybe we take a piece of chert, right? That's very fine-grained, microscopic crystalline quartz, the novaculite they call that, or the chert, and metamorphose that. That would become a quartzite. This is very durable, the quartzite. You get all manner of coloration with that as well. So say we took the chert as the parent rock, right? So basically it's a quartz mineral, that's silicon dioxide, kind of quartz mineral, and then we get the quartzite. Quartzite's very durable. It's almost a fused, interlocking look to the quartz grains in there, and very durable. The marble makes very beautiful tile. You think of maybe marble countertop or something like that. Here's some marble, variety of some marble, beautiful colorations, and you can get your quartzite's even more durable. If you want to get a nice kitchen countertop, quartzite is, if you can afford it, is the best because it's very hard, very durable. Marble, sometimes, yeah, we get that in our cutting utensils. We'll scratch it because marble's not quite as hard and durable. But your quartzite, these come in a variety of beautiful coloration as well, because you remember how the quartz had all manner of coloration in them. And so the quartzite, that's what you would want for a kitchen countertop material because it's so beautiful and durable. Okay, so where were we here? Yeah, so if you started with, say, a quartz or a sandstone of some sort, or the chert, yeah, because it's a quartzy material, you would end up with what they call the quartzite. Okay. The anthracite coal, so say you took some of that bituminous coal, or maybe some of that lignite, but remember that it went through different grades of coal. So we had the lignite, then we had the bituminous coal, and then the metamorphic offspring. So say you took the bituminous coal, okay, and you underwent metamorphism, you would get the anthracite coal. Okay, that one had kind of the sheen to it, sort of a shiny, goldish hue to it. I think I showed you the anthracite coal back in the introductory chapter when we talked about coal. So all of these, though, you're having a parent rock, and then it undergoes metamorphism, more heat, more pressure, and you get your offspring or your daughter product, kind of the metamorphic product. to it. So these are all usually a single kind of a mineralogy in them, and then it's just an equidimensional rearrangement or recrystallization of that mineral. So there's no foliation. So limestone, quartzite, marble here, they're not going to have foliation. No foliation here, equidimensional. It was our slate and our schist, it went away real quick there. The slate and the schist, go back one. The slate, schist, and gneiss were the ones that they showed us here for the foliated textures. So two broad textures, foliated and non-foliated, are how we classify our metamorphic rocks. That's the basis of it. So you have that figure in your PowerPoint. You might want to spend some time in looking at that. But here they're just talking about the common metamorphic rocks here that are foliated. Nice, strong segregation of those silicate minerals, so the banding. You're going to get the striation of those bandings happening on there. The non-foliated marble makes a good example of that. The parent rock is the limestone forming the marble. So it's an equidimensional interlocking crystals of the calcite. You kind of get recrystallized, a little bit larger size, and interlocking, three-dimensional, okay, sort of network there, marble. So it's definitely a non-foliated sedimentary or metamorphic, sorry, rock, okay, non-foliated. Okay, and I think that brings us, the uses here. We're almost done. So here we have the non-foliated rock of marble, filled in stone, variety of colors. I showed you just one little tile there. We like our marble countertops and such, but even quartzite's even better as a tabletop, kitchen counter tabletop. But for that one, you've got a quartz. It could be a sandstone. It could be the church. You know, something with quartz in it. So the silicon dioxide, and you get sort of fused quartz grains. They get recrystallized, a little bit larger and fused looking because of the heat and the pressure that they're undergoing. So, okay. Now they're showing you the beautiful marble. That's probably showing it better than the actual sample under the camera. But look at the little calcite, okay? The calcite mineral in there, recrystallized, interlocking, three-dimensional. So definitely no foliation on this. No alignment of the mineral. Equidimensional, so non-foliated. Marble. That brings us to the end of chapter 2. So that is our rock unit. Certainly enjoyed sharing the rock samples with you. Don't know how well they were showing up under the camera for you. But if you are in lab, you will get an opportunity to get up close and personal with your rocks. But that brings us to a good stopping point, because our next topic is going to be plate tectonics. And so getting the foundation of our minerals and the minerals building up our rocks, now we're ready to take a look at what is going to happen to our rock material when it begins moving on these plates, the plate motion of plate tectonics. So it's a good place to stop. And again, if you have any questions, please get with me. It's nice to have these videos so you can go back and stop it and review it as many times as you need to. So I will see you next time. So bye for now.